I will try to guide you through the recent experiments that we have done. And do I point this thing at my friends on the other row? Yes, you can't see it. You certainly cannot see it, but anyway. And how do I progress from one slide to the other? Oh, right here. Amazing. Very good. So quantum limits of knowledge, it sounds a little pretentious, but let's see how we go. The cornerstones, the EPR entanglement and Bohr's complementarity, we all know and love it. And now we have this little guy, which is not that old, and it's called the quantum reference frame. And so I will tell you about our quantum reference frames and how they affect the measurement without harming the quantum theory. Is that okay? Right. So the good old freshman physics, Heisenberg microscope. We want to observe the position of the particle. We need to scatter a photon from it. So we scatter it, but the photon and the particle are also waves. And so we have the uncertainty, and either we know where the particle was, or we know what the particle momentum is, and there is the uncertainty principle, which leads us to the standard quantum limit for the free mass, which is defined by the time of observation and the mass. And I will try to convince you that this is not the limit. We can go further than here is the thing that we have in the lab. So I told you about the quantum limit for a free particle, but it also exists for oscillators. So this is our best oscillator. It's actually a pretty good oscillator. It's engineered silicon nitride, little drum mode, carefully protected from the outside world. It has a size of a fraction of a millimeter. You can see it, and the thickness is amazingly small, and it's a fantastic oscillator. So for an oscillator, there is, of course, also the uncertainty principle, and therefore the measurement of the X imposes uncertainty on P and the other way around. And there is a quantum back action of the measurement, which doesn't allow you to measure precisely. So in the cartoon way, in this time frame, you measure X, which is the X times sine omega t, and you impose the back action on P. Quarter a period later, you measure P, and you keep going. And the more you measure, the more quantum back action you impose. And yet, as I hope to convince you, it is possible actually to measure both in XP, X and P, if you choose the right reference frame. So we call it trajectories without quantum uncertainties in a negative mass reference frame. It's also called quantum mechanics-free subspaces by Carl Caves and co-workers. And the idea is that we want to make a quantum trajectory look like a classical one. 3 steps towards this wonderful goal. You need to define the motion relative to a quantum reference. This reference should have an effective negative mass, whatever it means. And we need to create an entangled state of the reference and the probe system. And then we can make a measurement relative to this reference frame with unlimited accuracy in its trajectory. There is a long list of nice papers, and I cannot go through all of them, but it started with the very general ideas of quantum frames of reference by Aronoff and colleagues. And then 22 years ago, we ran an experiment where we actually used the negative mass idea without realizing it, but achieved some good magnetometry resolution, and so on and so forth. So let's look at this negative mass reference frame. We all know and love entanglement. So if I have two systems, X minus X naught and P plus P naught should be made arbitrarily small. This is Einstein-Podolsky-Rosen paradox, or rather not paradox, but entanglement. But so let's see what happens if we measure the position of our system as a function of time with respect to the other system x naught. And if you write down very simple kinematics, you will immediately see that this involves the difference of the two positions and the difference of the two momenta, and they don't commute. And therefore you have diverging trajectories. But if the effective mass of one of the systems is actually negative, then you have commuting variables defining your trajectory, and that's the story that I'm going to tell you. It's the same for the oscillators, except for now you also have the elasticity negative, the mass effectively negative, and the frequency effectively negative. And I'll show you an example in a minute, and you'll realize that it's not fantasy. Right. So back to the lab. You need a very good oscillator because you need to run your experiment in the quantum back-action limited situation. And our oscillator is as good as it can stay in a single phonon state for 1,000 periods. It has an amazing Q of 1 billion, and it's placed inside an optical cavity to enhance the measurement. And this is the actual machine. So again, unfortunately, the pointer doesn't reflect of this screen, but what you see in the upper left corner is the quantum back-action limited measurement of the motion of this little membrane. So you see it oscillates a little bit in this cavity, and the oscillations can be converted into optical signal. And this optical signal contains the phase shot noise of light, the signal itself, and the back-action noise due to the amplitude shot noise of the light. And we're absolutely dominated by this back-action shot noise. And this is important because if we're dominated by the back-action shot noise, that means that the shot noise of light is small compared to the measurement of the membrane we want to achieve. So, ladies and gentlemen, welcome the negative mass oscillator. It's a spin ensemble containing a gazillion of atoms, and they are all oriented in one direction in the Bloch sphere. And so the ground state of this oscillator will be like that, the uncertainty of the order of square root of the number of particles. And now if I manage to generate the first excited state of this oscillator by doing this, then the size of this first excited state will be larger than the size of the ground state, right? And therefore it will be a little closer to the South Pole and will have a little lower energy. And here is an oscillator where you add excitations and you reduce the energy. So that's a negative mass oscillator. And you put it in the magnetic field to make it oscillate, and life is good. So there are many incarnations of those kind of oscillators in the labs, and one of our incarnations is actually a thermal ensemble of atoms in a special spin protective environment. But those are kind of technical details. And what's important is that we can have this ensemble. It has a very high Q and a very long lifetime, and we can pump it in the all spins up and then generate the single excitation or other states, entangled states, for example, and they will all have the energy going down with the number of excitations. Okay, so let's measure now. We want to measure the quantum projection of the atomic spin, so we take linearly polarized light, we put our ensemble in the magnetic field, and we measure. We measure the polarization rotation, and the signal that we get contains the information about the spin, but of course also the back-action noise. And we want to be dominated again by this back-action noise, and we are, after some hard work. And now we have two systems, the atomic system and the mechanical system, and they are dominated by the quantum back action. And now we can run our experiment. So we send light through the atomic system and the mechanical system. And our measurement on this light contains the short noise of light plus two back action terms. And if we make the negative mass atomic oscillator susceptibility matching the mechanical susceptibility, but with the opposite sign, we can cancel the back action. And so we did. And in the upper left, you see the dominated by back action signal from the mechanical oscillator. On the right, the atoms. If you put them together, you have 6 dB, 6 decibel, that is 4 times reduction in quantum back action. So this is accomplished, and that means that we can actually go on, generate entanglement of those systems, and we have done that, again, using the atoms as the negative mass, and generating entanglement in the sense of this sum of the variances of the two systems going to zero. So it's essentially Einstein-Podolsky-Rosen entanglement, except for between the motion and the atomic spins, and the atomic spins are in the negative mass regime. Oops. Oops. Okay. Now it takes 2 clicks. All right, so I don't think I have time to walk you through this, but this is the experimental result. It's been published, it's now official. Damn it. Big. Okay, well, I would really love to show you the real-time trajectories of those two oscillators, but I don't think I can do it with this remote. But what you will see, what you would see, would be the two random trajectories of the two oscillators, which follow each other well within the Heisenberg uncertainty. So, sorry about that. So the two oscillators are entangled, and therefore they can be used for the measurements beyond the standard quantum limits. So in the remaining, 3, 4, 5 minutes, I would like to tell you about one application that we're working towards. We have used those principles for magnetometry beyond standard quantum limits and other experiments, but what's the most challenging motion in the world? Arguably the most challenging motion in the world is the motion of the mirrors of the gravitational wave detector. So the gravitational wave comes in and it rocks the two mirrors of this interferometer. It's a tiny motion, but it can be measured, and it's a signature of the gravitational waves. And those gravitational wave interferometers are now actually limited by the quantum noise of light, and in the lower frequency range of the gravitational waves, it's limited by the back action of light, and in the upper by the short noise. And so they have their own ways to mitigate this noise, but we're free to do our own thing. So what we do is we want to combine this interferometer with the negative mass spin oscillator. It's not as simple as that, but this is the main part of it. It's the intricate cell containing long-lived spins, which can work as the negative mass oscillator in a magnetic field. And so in the ideal world, you would have a response of the interferometer and the response of the atoms with a negative mass. You put them together and you have a complete reduction of the noise, and all you have is the signal in the real world. And that's the simple arithmetics which show you that. I'm afraid I have to go through this real quick. One thing to mention is that we cannot use one and the same probe to entangle those systems because atoms need one color and gravitational wave interferometer needs the other color. Therefore, we need to use entangled light to entangle those systems. And using entangled light, we can hopefully achieve that. So in the lab, we're building this part, and then we simulate the interferometer response and hope that if we do it good enough, then it will be an attractive system, but not just for that. So yeah, I'm actually an experimentalist, believe it or not. This is the evidence of it. And our noise reduction machine for gravitational wave detection is relatively small compared to the 300-meter long filter cavities that they implement in gravitational wave detectors now. So we have basic steps implemented. We have generated entanglement between two different colors, one for addressing atoms, the other for addressing gravitational wave detector. We have observed quantum behavior of our spin oscillator at low frequencies. So how low is low? 18 kilohertz, 3 kilohertz, 1.7 kilohertz, 700 hertz. We're still not in the few tens of hertz domain that is required for gravitational wave detection, but we're heading there. So our loving eyes of father simulations show that we can suppress the noise with reasonable efficiency. And with that, I thank you for your attention.